Okay, so let's get started. Okay. So in last week, we have briefly learned MapReduce. So from this week, we will spend about 3 weeks to learn MapReduce programming. And I will also try to explain some internal mechanism of MapReduce to let you know how MapReduce is designed. So if you remember what we learned in last week, so we use word count as an example to show how MapReduce is used for big data programming. Okay, so this figure shows a brief data flow in MapReduce. And you need to remember that, so in MapReduce, mapper will read the input from HDFS. So HDFS is called Hadoop distributed file system. So in the lab, I think you have already practiced some HDFS operations, how to manage the files in the distributed file system. So all the files are managed by HDFS in Hadoop MapReduce. So the mapper will read the data from HDFS. And next, so in the mapper, the several map tasks will be started for the distributed data. So the data is partitioned into several chunks. So we will introduce details later about how the data is divided into small parts. So the map output is partitioned by key and then sorted according to the keys and grouped the values for the keys. And the grouped results will be sent to the reducer. And so actually sort, it's not very accurate that sort is in the reducer side. So in the mapper side, MapReduce will also sort some keys, some intermediate results. And in the reducer side, there's also a sort phase. So again, I will introduce the details in the later slides. So you just need to remember that after mapper, so the mapper generates some output for the input, and then the format of the intermediate output is in format of key and value pairs. And next, Hadoop MapReduce will group the key value pairs according to the keys, and then sort the keys. And then the sorted results will be received by the reducer. So in the reducer side, the reducer will process the grouped results and do aggregation, and then generate the final output to HDFS again. So the final output will be written to HDFS as files. So this is a very brief data flow. So the most important thing you need to know first is about the data structures in MapReduce. So everything in MapReduce is managed by key value pairs. So the key value pairs are the basic data structure in MapReduce. The key and values can be such as integers, floats, strings, and even raw bytes. You can also define your own keys. So you can define a class. and then let this class to be the keys. But you need to give some way to sort the class objects. So these are the keys. And for values, you can also define your own class, but you don't need to give the sort functions for the values class. And we can, we will learn how to customize your own class for key and values in maybe next week. So for the MapReduce algorithm, in order to design the MapReduce algorithm, you need to first think about what kind of key value structures you need to use for the input and also for the output. For example, for a collection of web pages, you need to think about, so what will be the input keys and values? So for the web pages, and it's very easy to identify the keys. So it could be the URLs, because the URL can uniquely identify each web page. And the values, just the HTML content, just text with some HTML text. In some algorithms, the input keys are not used. For example, if you, so we will see the word count example. So actually, the input key is not used in the algorithm. But anyway, you need to follow this data structure. You need to make the input as a format of keys and values. And the keys and values will be read into mappers automatically by MapReduce for later processing. And the keys will be combined in complex ways to design various algorithms. So for MapReduce programming, remember that, so in last week we learned that you need to give MapReduce functions about how to do the map, how to do the transformation, how to transform the input into some intermediate results. And next, you need to tell MapReduce how to do the aggregation in the reducer. So how to reduce the intermediate results from the map output and to generate the final output. And so actually before that, you need to first think about how to design your key and value structures. What should be the key data type and what should be the value data type for both input and for the output. So formally, what you need to do is like this. You need to give two functions. First is the map function. This map function takes two parameters. One is a key and another one is a value. So we call the key1 and v1. And the output is a list of key value pairs for the mapper function. And it means that the map function will transform the input key value pairs into a list of key value pairs for later processing. So in word count, in the word count example, the input is a document ID and the document content. And the output is a list of term as a key and one, the value 1 as a value. So that's in the word count example. You also need to define another reduce function. The reduce function will also receive a key value pair. It's called key2 and a list of values. So this is obtained by a group by process in MapReduce. So MapReduce will group all the values for the same key. So for example, in word count, each term from different mappers, they all have the same key, right, for the same term, but with the value 1s. So in MapReduce, they group all the 1s for the same term. And the reduce function will receive one term and a list of 1s, which represents the count of this term. And output, this is the final output. The final output is also in format of key value pairs. So the reduce function will aggregate the list of values for each key. So your aggregation works on the list of v2, a list of values in the input of the reduce function. And all the values with the same key will be sent to the same reducer. So the values for the same key will not distribute to different reduce functions. So they will be sent to the same reduce function for processing, for aggregation, to generate the final output. So that's what you need to do, map function, reduce function, and about input data type, key value pairs. So what should be the key type, what should be the value data type, and in the reduce function, and you need to think about what will be the output key value pairs, K3, V3. So for the other things, then the MapReduce environment will take in charge of them. So for example, some low-level details about how to deal with the failure, how to do the, how to assign the jobs, the map job and the reduce jobs, and how to start them, how to schedule them. So all these things will be taken by MapReduce, the framework. And so for MapReduce programming, and finally, actually, it is such a complex program that can be decomposed as the MapReduce tasks. And sometimes you need to have the change MapReduce tasks. So which means that map and reduce will have some output, and next this output will be read by the next round map function, and then reduce, and then the next round map reduce. So the change map reduce job is usually used for graph algorithms or for machine learning algorithms, which requires iterations. So we will again see some examples in the following few weeks. So I know it's still a little bit not very clear, right? So let's look at some examples. So this is, again, this is about structure or the data flow of MapReduce, but with data types. So first, the map function will receive a list of key value pairs for processing. That read from input, and then it generates a list of key value pairs. And next, so this is what MapReduce will do for us. So we do not need to care about the shuffle and sort. So the shuffle and sort just means that, okay, the MapReduce will group the values of the same key, and then sort is for the key sorting. So keys will be sorted. And then the sorted result will be sent to the reducer. The grouped and sorted result will be sent to the reducer. So the reduce function will receive a key and a list of values that are obtained from the map output, and then generate the final output. So the aggregation works on the list of P2 and to generate the final output. And the data flow is like this. So input is in format of K1, V1. So using word count as an example, K1 is a document ID, and V1 is the document content. And after the map function, so the map will transform the input to a list of key value pairs. So here, in the word count example, it would be the term and the value 1. So a list of terms in the document, in the input document, and the value are the integer 1. And so about combiner, we will explain later. So after the shuffle and sort, we will have a list of key and a list of values for this key. So each reduce function will process one such key value pairs to do the aggregation and to generate the final output. So in the word count example, here K2 is one term, and a list of V2 is a list of ones for this term. And in the reduce function, you just need to sum all the ones for this key. So it is a final count, the final frequency of this term in the input document. So the final output, K3, is a term as well, and V3, it is a final count of this term in the input document. So it's the final output. So let's look at one word count example. So assume that we have some documents. So in this example, we have only 2 documents. And the documents can be obtained from different sources, such as tweets or blogs. So anyways, assume that we have 2 documents. This is your input. So your job is to count the frequency of each term in the document, in the input documents. So the 2 documents are Hello World, Hello Hadoop by Hadoop. In the input is in this format. So if the original format is not like this, you need to make some transformation of the input file to make it as a document ID and the document itself. So that we have 2 documents. And next, each map function will process one document. So each input key value pair will be processed by one map function. And so what does the map function do? Remember that so the map function will emit a key value pair for each term it meets. So for example, hello, and the output of this map function will generate hello 1, this key value pair. And for world, it generate world and 1. So this for the first map function. And for another document, so there's another map function to deal with this document. And for the 4 terms, then we have 4 key value pairs. So like this. So that's the output of the mapper. So the output of the mapper is in format of key value pairs as well. So this is the intermediate result for a word count job. And after shuffling and sorting, so the reducer will receive this format, K2, and a list of values. In our word count example, so the K2 is a term, and in this intermediate results, we can see that there are two hello and one, two such key-value pairs, right? So Hadoop will group the two ones as a list for this hello key. And so this is just a group result. There are two Hadoop, so there are two ones in the list. And by and world, they all for all the key-value pairs, the value is a list of values. But for world and by, there's only one integer one. So this is group by result. Actually, there's also a sorting result. If hello, if term is a key, so actually the order should not be like this. The order should be by one, then Hadoop two ones, and then hello two ones, and then world one. So the keys will be sorted according to predefined sorting function. So this is the key is a term, is a string, so they will be sorted alphabetically. So this is input of the reducer. So each key value pair will be processed by one reduce function. So in the reduce function, so it will process hello and two ones. So what does the reduce function do? It will do a sum for the list of values. So for example here, for this key value pair, for this key and the list of values, so the reduce function will do a sum for the two ones, and the result is hello and two. So this two is a final count of this term in the input document. So this is a very, very easy example for you to understand word count. And now you can think about if you have a huge number of documents, right? So now we have only two, and you have a lot of documents. And this can be done in parallel. So it depends on how many computers you have in your cluster. So in the same time, each worker node will do some map jobs, will process some documents, and generate some intermediate result like this. And after all the map functions finish, all the documents are processed by map functions. So we have a lot of such key-value pairs. And MapReduce will group these key-value pairs and in this format, and then sort them according to the keys. And then each key value pair in this format will be sent to a corresponding reducer for processing. So you can also have many reducers to do aggregation in parallel. So how many reducers you can use also depends on your own requirements. So finally, you have the result stored in HDFS. So this will be written to HDFS. It's a brief data flow for the MapReduce word count. Oh, sorry, it's not just mapper, both mapper and reducer. And that's why MapReduce has very good performance, because in both the mapper side and the reducer side, you can do the tasks in parallel, right? So for different documents, you can process them in different computers in the same time, and so some intermediate results will be generated. And then next, in the reducer side, so the reducer can also do the aggregation jobs in parallel. So they can do the sum for the values of each term to generate the final output. And finally, you will receive the final result. And this is definitely much faster than doing this job on a single computer. Okay, so this is another brief view for MapReduce. So what we have, remember, is key value pairs. It's the input. And the key value pairs will be sent to different mappers and for the map functions to process. And each map function will deal with one input key value pair to generate a list of key value pairs. So for example, here we have each map function generates two key value pairs. And next is it's a job of MapReduce, not the job of us. So MapReduce will do shuffle and sort. It will aggregate the values by keys and also sort the keys. And next, the corresponding key value pairs in this format will be sent to the corresponding reducer for processing. So each reduce function will deal with one key and list values, such pairs. And aggregation will be performed over such input to generate the final output. And next, this final result will be written to XDFS. But it's just a very brief view of MapReduce to make you to have a very basic understanding of MapReduce programming. And okay, so about shuffle and sort, I want to talk this a little bit more. Actually, it is much more complicated. And after explaining the MapReduce programming, I will try to show you more details about this step. And shuffle, in the shuffle step, you can just think about this kind of, how to say, so a group-wise kind of in this phase. So the input of the reducer is a sorted output of the mappers. So mappers generate some intermediate results, and the intermediate results will be grouped and sorted, and these are the input of the reducers. So in this phase, the framework will fetch the relevant partition of the output of all the mappers using HTTP protocol. So the reducer will go to all the mappers to get the relevant data, and then merge them and as an input for the reducer. So it's kind of the shuffle step. And for sort, so the framework will group the reducer input or the mapper output by the keys, and then sort the keys. So the Hadoop framework will handle the shuffle and sort step, so we don't need to care about how the shuffle and sort are performed in MapReduce. We just need to know that there's a shuffle and sort phase in MapReduce. So your intermediate results, the map output, they are grouped and sorted, and then reducer will get the grouped and sorted results for the later processing, for the aggregation. So in this figure, actually, assume that we have 3 mappers, okay? Each mapper will have some output. So you can think about, you still use word count as an example. You can think about one large document file, a data set. It is split into 3 parts. So each part is processed by one map function, by one mapper. And the mapper will transform input into a list of keys and ones, the input, the intermediate results. And now think about one term, okay? For example, sort. So this term can appear in all the 3 mappers, right? So as a result, the sort and one such equivalent pairs could be here, here, and here. But each key should be only processed by one reduce function. So that's why the reduce function, the reducer, need to get all the sort and one equivalent pairs from all the mappers, and then merge them as a single key value pair. The single key value pair is in format of sort and a list of ones. So this is a merge step. So in this phase, so reducer will fetch all the required data from the mappers using HTTP, and then merge them as input for the reducer, and then for the later processing. In summary, so we can use this pseudocode to represent the hello world, the word count program in MapReduce. So what we do in Mapper is that for each given input, the document ID and document, which is a set of terms, and for each term in this document, we emit a key value pair in this format, the term itself and the count 1. So it's just a mapper. And for you, this is your job, so you need to tell MapReduce that, okay, so this is my job, and I want to do this. In the reducer, you need to tell the MapReduce to do this aggregation like this. So in the reduce function, what you receive is a term t and a list of counts, ones. So your job is to sum all the ones. So just one for loop is enough to get the final sum. And then the final output is a key, the term itself, and the total count of this term in the document. So that's a very easy task, actually. So I show this figure again. So this is used in the last week's lecture to show you how MapReduce works. So let's combine with this pseudo algorithm. Now let's see how MapReduce works. So giving you some documents, okay, we have, well, in this example, we have 3 documents. And so remember that first, this original data set in this example is not in format of key-value pairs, right? So what you need to do is first you need to give a key for each document. So actually, after splitting for each document, you should also have 1 document in order to MapReduce be able to process your input. Okay, so for each input key-value pair, the document ID and document, and according to the mapper, so for each term in the document, you will generate a key-value pair for this term, which is the term itself as a key and the value 1 as a value. So we have this output for this document, and output for this document, and output for this document. So that's all. And next, here, this is the shuffle and sort phase. So the keys, key-value pairs that are grouped together, and we can see that the same key-value pair, the key-value pairs with the same key, they are grouped, and also they are also sorted. So in this example, we can see bear, car, deer, and river. So they are also sorted. And next, each such key-value pair, the bear and at least once, will be received by 1 reduce function for processing. And the aggregation is like this, just sum all the ones. So the result is bear and 2, car 3, deer 2, river 2. And this is the final output that stored in HDFS. So for word count, it seems a very easy task in MapReduce, right? But for a lot of other tasks, actually it's not very easy to design the map functions and reduce functions. You need to be familiar with MapReduce programming, and then you can get used to this kind of a paradigm for programming, and then you are able to design MapReduce programs for your jobs. So in the next few weeks, I'll try to give you a lot of examples for you to taste how MapReduce programming is like. And in the labs, you're also given a lot of problems. So I hope you can try your best to solve these problems on your own. And I will also show you the solutions maybe 1 or 2 weeks later after the lab. Okay, so next I will begin to introduce about the real programming. So before that, I'm not sure if you already understand the word count example. So are there any questions or any problems? No? Okay, so then I will proceed to the next section. Next is about how you can write the program in MapReduce. Okay, so what I show here is just a pseudocode. And how to implement the word count in MapReduce. In the labs and in the projects, so what we use is the Java. So I'll suggest you to use Java because it's the native language for MapReduce. But if you like, you also use Python or even C++. But I think it's not that easy. You still need to use some. You need to implement more steps in order to make them run in MapReduce. So please try to use Java in both labs and projects. For this word count program, what we need to do? So remember, we need to think about the inputs, the key value pairs. What should be the data type? So for the key, is a document ID. It's just a unique identifier of a document. So it depends on the input size. If it is not that large, so integer is already enough, right? Otherwise, you need to use long. And document is a set of terms. So it's just a text document. And mapper will take the input key value pair and tokenize the lines, tokenize the document into terms, and then emit the intermediate key value pairs. So for the framework, it will do the shuffle and sort, and then guarantee that the values for the same key will be grouped and will be brought to the same reducer for processing. And the reducer will receive all the values associated with the same key and then do the aggregation. So how to write this in Java? So for MapReduce programming, you mainly need to write the following 3 classes. The first is a driver class, or called main class. This is where you can configure the job and where you can start the job. So this will trigger the MapReduce methods. And also need to write the mapper class. So this defines how the map function is like, how you can transform the data into the intermediate results. And next, the last one is reducer class. So in this reducer class, you need to give a reduce function. So to tell MapReduce how you will do the aggregation to generate the final output. So it is better to include MapReduce and main methods in 3 different classes for the larger jobs. But for the word count program, you can also write them in a single file because it is not very huge. What you do is you can check some detailed information for all the classes at this web page. So it gives you a lot of more information about them. And now let's look at the mapper class. So I'll just show you the raw code here. I think without explanation, it's not very easy to understand, right? And if you are familiar with Java programming, okay, and you can see we have a class and extend something, some class. According to name, it should be a mapper. So this is our mapper class. And we have some 2 variables, but you see some unfamiliar classes, interactable and text. They are not in Java, right? So actually, there are some wrapper classes in Hadoop MapReduce. Why MapReduce needs some new classes for the data types? So we need to explain them later because MapReduce is based on HDFS. Remember, it is based on the distributed file system. It's not based on a local file system, which means that it needs some new ways of doing the synchronization and serialization and deserialization. Okay, so next, so we have a map function. So you can guess it is where you can tell MapReduce how to do the transformation. And okay, here this is about we have a string tokenizer, and this tokenizer will tokenize a given value, which is document, into the list of terms. And for each term, and we generate a key value pair, the word as a key and y as a value. Okay, so the structure seems easy, but we have a lot of unfamiliar classes, right? So I'll try to explain them line by line. In your MapReduce programming, mapper programs, you also need to define a mapper like this. You always need to define a mapper like this. And first, it's about what is the class header. You need to extend from the mapper class. And in the mapper class here, you need to fix the data types for your input, for your mapper input key and value pairs, and also for the mapper key, mapper output key and value pairs. Okay. So in this example, so the input key value pair is object. So we use object here because we do not use the document ID in the word count example. So it doesn't matter what kind of class we use. So you can also use long. Okay, here should be long writable in MapReduce. And we just need to get some object to receive document ID, but it is not used, so we don't need to give more detailed data type. And here, this is the data type for the values, text. Actually, this is a MapReduce string wrapper. And you can think about this as a string in MapReduce. The document itself, and for the output, so remember in word count, the word output is term and one, right? So the key is also in format of text, and the value is in format of interactable. So for the class header, you need to extend the mapper, and also you need to give the data types for input and output of the mapper. And so formally, the class mapper has 4 parameters. So the 4 parameters correspond to the key in, value in, key out, and value out. So in the word count example, it's like this. And the interactable and text as a site, there's some wrapper classes in Hadoop MapReduce to wrap the basic data types in Java. So interactable is a serializable and comparable object for integer. So now you can put your integer into this class, into an interactable object. Now Hadoop can serialize this integer to HDFS. And also they can be compared. And this is a comparable class. And in our program, so we define value 1 with an iterable class. And text, it stores strings using the standard UTF-8 encoding. So it provides methods to serialize, deserialize, and compare text at byte level. So you can think about text as a string in MapReduce. So remember that you can't use the basic data type in Java in MapReduce programming. Okay. Otherwise, MapReduce is not able to serialize your data into HDFS. It will cause some exceptions. So you can try in the labs. You can try if you do not define your data type like this. So next week's lab, you will practice word count and some other programs. You can try this. Try to use some use basic data types. And Hadoop supported data types for the key value pairs can be found in package in this package rg.apache.hadoop. So all the data types are supported in this package. And the two variables are used to store the values and the keys. Okay, the keys are terms and value is 1. So we already defined them. So what is a readable? This will be also be explained in details in next week's slides, but here I briefly introduce about this readable concept. So Hadoop defines its own box classes for strings or wrapper classes for strings, integers, such basic data types in Java. So all the values must implement interface readable, and all the keys must implement interface readable comparable. So the keys must be comparable as well, but values could just be readable. Readable means that they can be written to HDFS by Hadoop MapReduce. So readable is a serializable object which implements a simple, efficient, and serialization protocol as provided by Hadoop MapReduce for us to use. And okay, so that's for the header. Now we go to the map function. So let's look at the map function. And the map function takes 3 parameters. The first two are input, key, and value data type. So the input is a document ID and document, right? So it's object key and text value. And this context object, this class stores the output for your map function and also some other environment variables for this map function. And you need to use this context object to write your mapper output to the file systems. And this is an inner class of mapper, so it is used to store a lot of context of running a task. And in the word count example, this is very simple, right? So we just use to collect the data output. And in the reducer, we also use this object to collect the final output. And we also need to throw some exceptions. So this function is called once for each key value pair in the input for the input data, and which means that for the word count, each document and document ID, each key and value this pair will be processed by one map function. So you can see this map function. So it reads one key and one input document, one value, right? So which means that each key value pair will be processed by one map function. And this is the main job you need to do in MapReduce programming. You need to override this map function. And this tells MapReduce how I can do the transformation for you, how I can transform your input data into the desired data type, desired intermediate results for later aggregation process. So within the map function, okay, so first we use a string tokenizer to tokenize the documents, to tokenize the string. So it's kind of split the strings according to some characters. So by default, it is based on the space and type characters. Now the documents will be split according to the space and types and into the terms. So next, we just need to iterate through each word and form a key value pair for each term. So for example, if there's a next token, so which is the next term, then we set the key as this term into this word, which is a text object, into this word object. And now we can write one key value pair out to the file system. So this is the term itself and one count of this term in this input document. So that is a map function. So as a result, given you a document for the map function and a list of term and one such key value pairs will be written to the file systems by this context.write, by this comment. So the map function will produce a map context object, and then this will take key and value pairs as an input. And so should remember that for the keys must be writable, comparable, and for the values it must be writable. So as a result, the keys can be sorted by MapReduce because they're comparable, and they can also be written to the file systems because they are writable. So it's very important. Remember, you can't use the Java basic data types such as strings or integers or float or double. If you use these data types in your MapReduce programming, you will get some IO exceptions because MapReduce is not able to write your data to the file systems. Okay, so that's a mapper. And next, let's look at the reducer. Again, the raw code here is not very easy to understand because you still meet a lot of unfamiliar classes, right? Such as the reducer class, but you can guess this is a reducer class. And with knowledge of the mapper class, now you can guess the four data types, right? So this is input data type of the reducer key value pairs, and this is data type for the final output key value pairs. In the word count, it receives term as a key and a list of integers. So here is a text and interactable. And the final output is a term and the final count. So it's a text and interactable. And your output, your data must be consistent with such data types. Otherwise, we also have some IO exceptions. So in the reducer, and it's very easy, we just do aggregation over all the over the list of values. So here is a reduce function, and it receives a term and a list of integers, and then the final output is again collected by this context object, and we do a sum. So here we can see the same context.write key result. So this is the final output. The final output will be written to HDFS. So that's a reducer. And again, let's try to see look at code line by line. First, you need to define your reduce function. The reduce header is similar to the one in the mapper class. Okay, and you need to extend your own class from the reducer class provided by MapReduce. It will tell MapReduce that okay, this is a reduce class, and you also need to define the data types you used in the reduce function for your job. In word count, because input is in this format, right? A term and a list of integers. So this is a text interactable. And the final output is term and final count, so text interactable as well. And this reduce function, you must override this reduce function in your own MapReduce program. So this will tell MapReduce how to do the reduce job for your task. So in the word count example, and what you need to get is to sum all the values in the list, right? So we just use the for loop to get the sum. And then this should be stored in the value, in the result object. So the result object is defined previously. It is interactable object. And then we can write the key, the term, in format of text, and the result in format of interactable to HDFS. So this is a final count for this term in this key. So it's a reduce function. And mapper, reducer, and last one is a driver function, driver class or the main class. In the main class, so you can see some lines, you do the following things. First, you need to configure a job. You need to configure your job such as what is a mapper class, and what is a reducer class, and what is you need to give a name for your application, and what is input and input key and value classes, and what is output key and value classes, and you also need to give the input path, output path, and then you start your job. So a lot of things you need to do in this main class. Okay, so in our word count, so let's look at what we need to do. So first, we need to give a configuration object to do the configurations. We need to new configuration object, and then so we use the job object to get the configuration to initialize the configuration object, and oh, sorry, we need to use the configuration object to initialize the job object. Next, we need to use this job object to do all the configurations for your task, such as what is a jar class name for your jar, and what is a map class, reduce class, output key class, and output value class, and input path, output path. So input path is provided in your parameters of the main function, and output here, the output path is also obtained from the parameters of your main function. And finally, you will start your job here, wait for completion, which means that your program will wait for the completion of the mapper tasks and reducer tasks. So what you can do here now at this stage is just to wait for all the tasks finish to see the final results on HDFS. And I'm not sure if you have finished lab 1. So in lab 1, I didn't ask you to write the word count, but you can use existing word count program. You can compile them and run them in MapReduce, and you can see the output in HDFS. So if you see you have finished lab 1, you should try to connect lab 1 with what you have learned at this stage. So after you run your program, which means that so the entrance of your MapReduce program is here, is the main function, and then it will first configure your jobs, and then get input path, output path, and finally it will start your job, and you can see a lot of output in your screen, right? So that's how MapReduce is running your job in your cluster, but actually you do not have cluster, it's just a pseudo cluster. And after you see some kind of successfully, the job is completed successfully, then you can go to HDFS to check the output of your job. So here are some more details about the main function. So given the mapper and reducer code, and this main function will start your MapReduce job, and the Hadoop system will pick up a bunch of values from the command line on its own, and then this function will specify a few parameters for a job. And this job object is a primary interface for you to describe the MapReduce configurations, and in order to make the Hadoop framework to execute your job according to these configurations. And the other parameters, such as the number of machines to use, they're optional, and the system will determine some default values for you if they're not specified. And then the framework will try to execute the job. So here you can see that actually we do not define how many mappers we want to use and how many reducers we want to use, right? So which means that there are some default values for the number of mappers and number of reducers. So by default, the number of mappers depends on your input data. So that's why you can keep this question in mind, and we will explain in later slides. And for the reducer jobs, if you do not tell MapReduce how many reducers you want to use, so by default it is just one. You will only have one reducer. So which means that there's no parallel processing in the reduce phase. And if you want to use more reducers, you need to have a job.set number of reducers, such as 2, 3, 4. Then the Hadoop program framework will know, okay, and your job needs these reducers, and then it will assign the corresponding reducers for you to use. But by default, it's just one. I have already explained some details here previously, actually. So let's look at if we can do some more explanation. So in the main class, so we need to create a configuration object and a job object. And we also need to assign a job name for your application. So this name will identify your application uniquely. So here, for example, we use word count as a name for a job. And this job class will allow you to configure job and submit the job and control the execution. And also, you can also current the state of the job execution. And so that's what we need to do before we try to start MapRun Reducer. And next, we need to set the job star by the class name. So the jar will be, this corresponding jar will be created. And we also need to provide the mapper and reducer class name. So this is the map class, reducer class. And next, we need to do some other configurations, such as what is the data type for the output key and output value. So remember, this is what count. The final output is a term, which is a text, and the count, which is integer, but wrapped by interpretable. So we need to specify them. And here, we only gave the final output, which is also the reducer output. But remember that the mapper output should also be specified in most cases. Here, we do not specify them. It is because the mapper output and the reducer output, they have exactly the same data type. Okay, so only if the mapper and the reducer, they have the same output data type, then you just need to you only need to specify the final output key and value classes. But if the mapper output and the reducer, the final output, they have different data types, you also need to configure the mapper output key class and the mapper output value class. So you will do this in some lab problems. So because previously I forgot to mention this, and a lot of you made some mistakes. So remember, when the mapper output and the reducer output, they have different data types, you also need to configure the mapper output key class and mapper output value class. But here, because in the word count, they have the same data type, so we just need to configure one of them. Okay, and next is about input path and output path. So they are obtained from the parameters of the main function. And next we start the job. So that's it. And next we can make it run. So this is program. And because word count is very easy, so we just put all the three classes into a single file. And for the different the classes, we use public static class in order to make all the classes into a single file. So there's some configurations. The more details are already given in the first lab. Okay, so next you can compile them using some tools by MapReduce, and then you put your jobs, your files to HDFS. So this is some operation HDFS, DFS put. So this will put your input file to HDFS. And then next you can run your application by using Hadoop jar, this comment. And you need to tell this comment what is the jar name and what is the main as class name and what is the input path and output path. And next you can see the results in the HDFS output folder. You need to use some HDFS comment to check the results. And okay, so that's how you can program the word count program in MapReduce and how you can make it run in MapReduce. So if you haven't finished lab 1, please follow the instructions because next week we will release the first assignment, and you need to make the environment ready. Okay, and I also need to clarify that the configurations of an installation of Hadoop MapReduce in the lab is not a complete instruction. Okay, if you want to install Hadoop on your own computer, these instructions are not enough. You need to do some other configurations. So the virtual machine image, it is already pre-configured for you. So that's why you just need to follow the partial instructions in the lab in the provided lab instruction file. So as mentioned in the lab instruction file, so some more details about how to do some other configurations, you can go to the Hadoop homepage and follow their instructions if you want to install Hadoop on your own computer. But anyway, as I suggest, you can first try to be familiar with MapReduce programming. And after you are familiar with this, then next you can begin to practice some more complicated jobs, such as how to install Hadoop, how to do some more complicated configurations, and yeah, okay. Okay, so have a break first, and then next we'll begin some new topics. It's okay to remove that. It's not a bad program. The study means that this data will be preserved for the other objects. Okay, so from the objects, you will clearly see the same result of the same value of the just some kind of Java rules. Escape. But anyway, so here you can think about it. It is no problem to remove the final step. Not objects.他说，我想就是说，静态的讲，那不好意思，我再把它放进去，我找一找。还有，我就说，觉得是不是因为它下面那些 map 啊不，你直接把这个倒进去，这个只是两个，内部这个是这个意思是说，这个这个光操作系统这个能放，然后是说你要想操作的话，就这个自己装好这个东西。但这个事情刚好它就是一个静态的电量不放静态的，对啊，我可能就是不好意思，虽然我就可以，虽然是不方便，但是我也放了一下。Just about the one set. If I make the directory under the DFS, this one will be the default working folder. So I don't need to put like a prefix. No. I can run it directly, but I try on my own virtual machine. Like, so I still need to put the prefix on it to run the command. Is that something about the version? No, not the version problem. I think some configuration problems, but I'm not sure. Yeah, I'm trying to find the configuration for the directory, but. Okay, so this is not the virtual machine image, or is this a virtual machine image on your computer? No, I configured it myself. Okay, so that's what the problem. Because this is a account name in the virtual machine image, so you need to use your own account name. So what is because I'm assuming that this is not the actual file system, it's XDFS.
So I just put the same username here.
No,
It should be my username.
Oh,
right?
okay. So where's the left instruction file?
It's here.
Okay, so I think there's some confusion from options. Specify the home folder.
Getting XML file the environment variable.
I'm not sure if I remember correctly. It should be consistent with the username on our machine.
我问 tutor，他说是因为你初始化的时候，就是说你初始化这个它就是一开始是没有那个登录的，然后
在开始 create 之后是有跟登录，只是说这个 folder 是没有建出来，后面能把这个 folder 建出来。
那他这里为什么默认？我当时也问他这里面为什么可以默认直接就这里就不需要打了，然后他说是什么？
我是觉得可能是有哪个
configuration 啊，
对，但是找不到。
我是这样的，应该是说是这个 username 是因为是你的跟你的那个自己那个机上的那个 account name 是一致的，然后 by default 的话这会变成一个那个 working folder。library 里边没有写嘛？我记得当然这个可能时间很长，我会帮你看一下。就是说你现在这边还不行，对吧？
对，因为我的那个我是没有按。
你这里用了你的 username？
不是，我就用了
那你试一下用你的 username。
你可以试下你的 username 建个试试看，在哪里？
要不然它就是默认的，就是 user 一杠你的 username。
你可以试一下 HFS。你的 username 是 team 吗？对 ，team 是吧？
就 TI。
错了。这样可以对吧？
那就是默认的它的 user。
那个需要跟你的 username 是一致的，所以它在那儿。我跟那边可能不清楚。Next hour. It's not a function, it's an extent. Because MATLAB tool is a lot of and pairs, right? And you have a lot of markers. It means that you have a lot of field pairs that they are in different orders. The input will be split into different chunks. Like bar, like yeah, that's right.
Who's responsible for
MapReduce. So it's more details. Again, it will be explained in later slides. So okay, I can talk about the briefly about the problem now. So the steps is so you have lab, right? So this lab itself is stored in HFS. A lot
Or I can say predecessor document.
Yeah, access document. Yeah. And then this left file is called XFS. And yeah, each chunk corresponds to one set of blocks. So now we just need to right set up the files position different parts. And each part has some position.
But each chunk means like let's say chunk 1 has
Yeah, something like that. Chunk 1 has some documents, something like that.
chunk 1 is document labeled document 1.
Maybe 1 to 10, maybe 1 to 10. The next chunk is maybe 10 to 10, 20, something like this. Yeah. And now each network will access one chunk. So some of the data is processed by each chunk. And now the next document will call document 1 is processed by another document. That document also. Okay, so anyways, for this chunk, we just need to remember with such a chunk and generate a lot of different pairs. Like another chunk, so another method, also generate a lot of different pairs. The problem is that now we need to group the pairs, right, for the same. But since they are featured into chunks, right? Sharp and tall sharp methods. In order to group the pairs of the
Shuffle for the method. Not for the
after the methods, yeah, that's right. After the methods. And the values for each of the groups. The sort is method is sort according to your breakpoints function.
why is this
Oh, because in word count, remember when you meet the term, you just only return when one. So the here, so what is this one?
factor to word something? This one
Here means this one. Just one. Yeah. I try to explain that because they have a better mistake. Okay, so I just have questions. In the next page, we can come to
Okay, so let's continue. I know you still have some confusion about MapReduce programming, although MapReduce example is given to you. So I'll try to explain more using one more example and more MapReduce details to make you have a better understanding of first about MapReduce framework and also about MapReduce programming. And so, okay, so by now, what we have seen so far is about what we need to do is we need to define the mapper class, reducer class, and the main class, right? But actually, in MapReduce, we also have some more classes we can use. The first one is called the combiner class. So often, MapTask will produce a lot of pairs in the form of key value pairs, right, for the same key. And so in word count, let's look at one example. Okay, here. In word count, so let's see in document 2. In document 2, we emit hello 1, Hadoop 1 by 1, Hadoop 1. Yeah. And in this output, actually, we can see that the same key value pair, it is generated twice, and they are sent to the reducer, right? So the combiner class aims to combine such key value pairs. So it can reduce the size of the data you need to send to the reducer. So that's the idea of the combiner. So with the combiner, what you can do, what we will get is here we will have Hadoop and 2 as a map output instead of 2 had to put 1 keyword pairs. So that's the idea for the combiner. And let's look at more details. So in the word count example, so if we just follow the previous program, then for a popular term, in a document, we have a lot of such terms, right? So which means that we will have a lot of keyword pairs with this term and 1 for this term, a lot of such keyword pairs. So this is a kind of a waste of both the data storage and the network transformation. And combiners is a general mechanism to reduce amount of the intermediate data. So this can save the network transformation time. And it can be think of sort of as a mini reducer, and still do the similar jobs as a reducer, but it's just a local aggregation, not as a reducer, which is a global aggregation. Okay, and the use of combiners, they are just optimization. Okay, this is optional in Hadoop. So the correctness of the algorithm should not depend on the computation of the combiners. So this is very important. So it means that your program should be correct whether you use or do not use a combiner in your program. And a combiner operates on each map output key, so it must have the same output key value types as a mapper class. So it also reads the mapper output as input. Okay, so it's just the same as a reducer. So the reducer receives reads the mapper output as input. The combiner also reads the mapper output as a input. And the combiner can produce some information from a large data set because it replaces the original map output. And this output of the combiner will be read by the reducer. So the output data type of the combiner must be consistent with the input data type of the reducer. And the input data type of the combiner should be consistent with the mapper output keyword pairs. And so this is a design of the combiner for your program, and it works only if so sometimes we can use the reducer as a combiner, but only if for your aggregation, the aggregation function in your reduced job is commutative and associative. And in this case, they can be used interchangeably. So which means that you can use the reduced class as a combiner class as well, but normally it is not. So I will show you more details about this part in the next few slides. So just need to have an idea about the combiner. So let's look at this combiner example in word count. And previously, we have some input. So assume that we have 2 data blocks, and each data block is processed by one mapper. Okay. So previously, without combiner, we will just have these key value pairs as a mapper output for the first block, and these key value pairs for the output of this data block. So that's for what we have done in the previous algorithm. And then the 2 parts will be shuffled and sorted and then sent to the reducer. So that's what we do previously. But now with the combiner here, so the combiner will work locally on the mapper output. So it will aggregate the key value pairs from the mapper output for the same key. So as a result, the key value pairs with the same key will be locally grouped. So B, we have 2 B and 1. So now it is combined as B and 2, and C1, D2, E1. And similarly for the next block, so another combiner will be used to do a local aggregation for this mapper output and to generate D2, A2, C1, B1. And after the combiner, the result will be shuffled and sorted, and then the input of the reducer is like this. For A, we have 1, 2. For B, we have 2 and 1. So without combiner, previously what we have is B, 1, 1, 1. We have 3 ones in the list. But now we will have just 2 values, 1, 2, and 1, 1. So this value 2 is obtained from the first mapper output by the aggregation of the combiner. So you can see that the values that are aggregated locally And the shuffle and sort here requires some network transformation. So if we can reduce the size of the key value pairs, so previously we have 2B1, but now there's only 1B2. So it will save your cost, your time of running your task. And now the reducer will do the same aggregation, just sum all the values. So the result will not be changed. And we can see the functionality of a combiner. So it aims to do a local aggregation for your local mapper output. So each mapper will have one combiner to combine its output to reduce the size of the intermediate results, which is output of the mapper. And then next, we can do shuffle and sort. So now in this stage, because we have used combiner and the data, the intermediate data that need to be shuffled and sorted, the size is reduced a lot. So the cost on shuffling and sorting is also reduced. So the efficiency of your algorithm can be improved by using the combiner. So it's the idea of the combiner, using the word count as an example. So using combiner, we can have much less data that needs to be copied and shuffled. So remember that the reducer needs to fetch the data it needs from all the mappers using HTTP. So with the combiners and such key value pairs are reduced, which means that the reducer needs to fetch less data from the mappers. So the network transfer can be more efficient. And if the combiners take advantage of all opportunities for local aggregation, we have at most M times V intermediate key value pairs. So M is the number of mappers. So if we have M mappers, so each mapper have one combiner. And at most, on each mapper, we will see V intermediate key. We will see all the keys, right? So assume that we have V unique terms in the collection. And so we will have C at most M times V intermediate key value pairs. But without combiner, and the size is not M times V. It is total number of the terms, not unique terms, but the total number of terms in the collection. So which is much, much larger than this value. And remember that on each mapper, actually, we cannot see all the unique terms, right? So in fact, in practice, the real number is much, much smaller than this value. So by using combiner, then the data size, the intermediate data size is reduced a lot. So in the word count example, so let's think about without using the combiner. For each term, you need to emit one key value pair, right? So the intermediate data size is just the number of terms in your collection, which is very, very huge. But with the combiner, now the intermediate data size is reduced to M times V. So M is the number of mappers, and V is the number of unique terms. So this is much, much smaller than the number of terms in your data collection. And this is the example about how combiners can will affect your word count program. So we still use the previous, if we use these two files, hello world by world, hello Hadoop by Hadoop. So if we use these two files, so without combiner, the mapper output is hello 1, world 1 by 1, world 1. But now the first map will have this as output is hello 1, world 2, not 2, world 1 key value pairs, just one key value pair, world 2, and by 1. And similarly, for the second map, it has output Hadoop 2. So the size of your intermediate data is reduced a lot. And so remember that in the word count, because the reducer and the combiner, they do the same thing. So we don't need to write another combiner class for the combiner. So we just need to set the combiner class as a reducer class. Then the MapReduce will use this reducer class as a combiner as well. So for the combine process, we will also invoke the reduce function to do the local aggregation. But this is because in this example, the reducer and combiner, they can do the same thing. But in most of the cases, in many problems, the combiner and the reducer they're not doing the same thing. So you need to write an extra combiner class. So when they can be used interchangeably, so remember we have these two keywords, commutative and associative. And I'm not sure if you know what is commutative and associative. Do you know? So commutative means that given a function f, and fab is equal to fba, so it's called commutative. And associative is that given a function f, and if there are three variables a, b, and c, so we can apply the function f to the three variables based on any order. For example, fa and bc is equal to fab is equal to fab, and c. So let me show you. Okay, here. I'm sorry, I think I need to restructure the lecture slides because I thought you know, but it seems that you don't know this. So commutative is like this. For example, this is a max function. So max function is select the larger value from the given input, right? So max AB is equal to max B and A. So this is called commutative. And associative is that giving you three values. Again, you want to get the maximum one. So you can first get the larger one from A and B, and then from the result of max A, B, and C, then you select the larger one. So this is the final result. But you can also do this by first by selecting the larger value from B and C, and then compare with A, and then select the larger one. So the order by applying the function to the given input does not affect the final output. This is called associative. So only if the problem is commutative and associative, then you can use the reduce class as a combiner class. But otherwise, you cannot do this. So more details. I will give you another example in the next few slides. So this is about combiner. So let's give a summary about combiner. So using word context example. So because for micro output, for popular terms, we will see a lot of the same key value pairs for the same term, for the same popular term, right? So the combiner aims to group these key value pairs for the same key in the same micro output. So this can reduce the size of the intermediate data. And this can further save the net transferring time to improve the efficiency. So this is about combiner. The next concept is called partitioner. And this partitioner is used when you have more reducers. So it's not very easy to explain the partitioner in this week's lecture, but I can show you the concept first. And next week, I will show you some problems. And in those problems, you must implement a partitioner in order to guarantee that your program can get the correct results. So what is a partitioner? What does a partitioner do? So the partitioner controls the partitioning of the keys of the intermediate map output. So if there's only one reducer, then you don't need to use partitioner. You never need to use partitioner if you just use one reducer. Okay, it is only used when you have more reducers to do the aggregation. So because each key must be sent to, all the values for the same key must be sent to one reducer for processing, right? So now the problem comes. There are so many keys with their list of values. So which key and their list of values, and its list of values should be sent to which reducer? So that's a problem. It's about how to partition the key space and then assign these keys to different reducers for processing, for parallel processing. And that's what partitioner do. The partitioner decides how you split your key space. So your keys will be split to different partitions according to a partitioner class. And each partition will be sent to one reducer for processing. So the total number of partitions must be exactly the same as the number of the reduced tasks, the reducers for your job. So if you have 3 reducers, for example, you in your main class, you set number of reducers to 3, then the number of partitions must be 3 as well. Because otherwise, some of your keys will be missed. There's no reducers that can process these keys, and the results for these keys will be missing. And so this controls which of the M-reduced tasks will process which intermediate key groups. And the system will use a hash partitioner by default if you do not give a hash partitioner for your program. So by default, there's a hash partitioner by applying a hash function. So if there are partitions, and then how to decide if a key should be sent to which partition, to which reducer, it is performed like this. So the key and get the hash value of your key and mod the number of the reducers, and then we have one value, right? So this value decides which reducer this key will be sent to. Why the partitioner is useful? So it's because in some applications, and we need to use this partitioner to to guarantee that the relevant keys are stored in the same file. So I forget to mention one thing. So if you use one reducer, you will have just one output file in HDFS. But if you have more reducers, so each reducer will generate one output file in HDFS. So for example, if you have 3 reducers for word count, and the word frequencies will be stored in 3 separate files on HDFS. So if you check your MapReduce output, you can see there are 3 parts, 0001, 002, 000, and 001, 002. You will see 3 such part files in your output folder. And the number of the output files is decided by the number of your reducers. So in this case, in order to guarantee that some keys, some results, they are in the same file, so we should control this by using a partitioner. So for example, assume that we are using some web pages as input. So for the web pages, the keys are the URLs, and the values are the web page content. And what we want to do is that we want to ensure that the web pages from the same host will be stored in the same output file, which means that they must be processed by the same reducer, right? So remember that the URLs, they are different. So for example, we have the USW faculties and USW maybe students about us. They're all from the same host, all from USW, from this host, but they have different URLs. So we wish that all such web pages will be stored in the same file, will be processed by the same reducer, but without applying this partitioner. So by default, the system will do this, will compute a hash value for this key. So the whole string as a key, and the whole string as a key. Then the hash value mod R to get the number of the partition. But because this is the whole string, the whole URL is used as a key, so we are not sure if the 2 hash values for the 2 URLs, they have the same hash value, right? Because they have 2 different, very different, so only the first few parts are the same, but the last few characters, they are different. So we can't guarantee the keys, the hash value of the 2, they are the same. So they may be distributed to different partitions, and they may be processed by different reducers. So what we can do is that we first guess the host name of the 2 URLs. So for example, for this one, we guess the URL, and it just www.usw.edu.au, and we just get this host for both URLs. So as a result, they will have the same hash value because they have the same host name. Then we only use the host name to compute the partition. So this guarantees that they will be put into the same partition, and they will be processed by the same reducer. And as a result, they will be stored in the same output file. So that's why we need a partitioner in some cases. And in next week's problems, we can see that in order to guarantee the results are correct, we must use a partitioner to guarantee that some key value pairs must be processed by the same reducer, and otherwise we are not able to achieve the correct result. So this is one example, and next week we can see some more examples about the partitioner. And in the word count example, we don't need to use partitioner because what we care about is just the term and the final count, the frequency, right? So it doesn't matter how the keys are split into different partitioners. So if there are 3 reducers, so we can just use a system default hash, this hash partitioner to partition the terms into different output files. So that's not a problem of the word count task. So now let's look at the MapReduce program, the framework again. So first, we must specify map and reduce these 2 functions. So this K1, V1, value on a key, is the input and the list of key value pairs. And next is the reduce. In the reduce function, it receives the map output, but it is a grouped and sorted map output. And each reduce function will process 1 key and a list of values to do the aggregation to generate some output, and also in format of key value pairs. And all the values will be the same key. They will be grouped together for the same reduce function to process. So this is very important. So this is the most important thing in MapReduce, and also where the magic of MapReduce happens. They group the values for the same key, and then they are aggregated by the reduce function. And next, optionally, you can also have a combiner class and a partitioner class. For the combiner class, and it takes the macro output is also in this format, and it generates a list of value pairs, and this is kind of a mini reducer that's running in memory after the map phase, and it's a kind of local optimization, local aggregation to optimize your task, to reduce the size of your intermediate data, and to reduce network traffic. So this is a combiner to do a local aggregation. And for partitioner, it is used to decide which key is processed by which reducer. So decide the partition for this key. And it also controls the load balance. Okay, because you have 3 reducers, assuming you have 3 reducers, right? You hope that each reducer can process a similar amount of data. So how to guarantee that each reducer can get the similar amount of data for processing? Actually, it's controlled by partition, but that's by the partitioner. The partitioner decides what data will be sent to which reducer for processing. And as a result, the load balance is controlled by this partitioner class. And often it's just a simple hash function of the key. So in the labs and also in the examples in our lecture, we just use this hashy partitioner. But sometimes, in some very few cases, you can use some other ways to define your own partitioner in order to control load balance. And also, it divides the key space for the parallel reduce operations for the parallel processing. Okay, so this MapReduce. Besides map and reduce these 2 functions, we also need to do, optionally we can also define the combiner class and partitioner class to improve the efficiency and to control the load balance, which is also which also aim to improve the efficiency. And so now some more details about the data flow. So in the previous slides, we didn't show that how to deal with input data. And there are some more details behind by MapReduce. So still use word count as an example, okay? So giving you a large file, the large file contains a lot of documents in format of document ID and documents. Okay, so this is the input file. How MapReduce will deal with this file, right? So first, this file is stored in HDFS. And HDFS is a distributed file system. But just like some other file systems, so the files are organized by blocks. But normally, distributed file system is used for large data set. So the blocks is much larger than the blocks in our the normal file systems. For example, in FAT or in some Linux file systems, maybe one block is just you can decide, but normally it is just one megabytes or 512 KB, and one block is in that size. But normally in HDFS, and block is much larger, maybe 64 megabytes or 128 megabytes. So, and this is about HDFS. And the files are organized by HDFS, and they are stored in HDFS. They are stored in different blocks. So naturally, the files are divided into different parts. They are distributed to different HDFS blocks. Okay, and in MapReduce, so the Hadoop will create one map task for each such block. So each map task deals with one input split, and each one input split corresponds to one HDFS block. So for this large data file, for this large document file, now it is split into a lot of blocks in the size of maybe assume that 64 megabytes. So if you have, for example, if you have 128 megabytes, a file like this in this size, your file will be stored in 2 blocks in HDFS. And in Hadoop MapReduce, so they will have 2 input splits. So each data block corresponds to one input split, and each input split will invoke one map task. Okay, so you will have 2 map tasks for your file. And next, in each map task, one map function will be called for each record, for each key value pair. So assume in your first block you have 100 documents, then your first mapper will have 100 times of map function calls to deal with these 100 key value pairs. And for your next block, maybe you have 50 documents. Then in the next map function, and the mapper, 50 map functions will be called to deal with those 50 key value pairs, 50 documents. So that's how MapReduce deal with your input. First, it will divide your input file into different blocks, or we also call it input split. And each input split will invoke one mapper or one map task. So this is created by Hadoop. And now you can see we don't need to specify the number of mappers. So the number of mappers is decided by your input size and your block size. And how many input splits decides how many mappers you will have for your task. And within each mapper, so remember that the map function deals with one key value pair, one record. Okay. So now, how to decide the size of the split is very important for the efficiency. A small size, a small block, is better for load balancing because the faster machine now can be able to process more splits, right? But the problem is that if the splits are too small, then we need to manage the splits. And manage overhead will dominate the total execution time, so we cannot make very small split. And so in HDFS, in MapReduce, so normally one split corresponds to one HDFS block. And so this can be configured. Normally it is 64 megabytes or 108 megabytes. So this is the whole structure of how MapReduce deals with the input file. And now, how to run the map task. So in MapReduce, we call this move the computation to the data. So this is different from previous distributed computation. So in a lot of previous distributed computation frameworks, they try to move the data to the computation. So there is a powerful computation cluster, and the data are stored in some data center. Then they try to move the data from the data center to the computation cluster. But that is not very efficient because the network is a bottleneck for your job. But in Hadoop, they try to overcome this problem. They move the worker to the data. So they move the computation to the data. So where the data is stored and where the mapper is performed on this node. Okay, and so this is also why the split size is the same as the block size, and each split corresponds to one HDFS block, and then this block will invoke one mapper to run to process this piece of data. And the map task will write their output to local disk. So it is not to HDFS. Remember, HDFS is only for the input and the final output, but not for the intermediate output. It's not for the intermediate results. This is because there's a lot of mapper outputs. And these intermediate results actually are not very useful after the aggregation. Right? And so once the job is completed, then the map output can just be thrown away. And storing HDFS is not useful as a kind of waste because HDFS has a lot of mechanisms to guarantee there's no to guarantee the guarantee the fault tolerance, just in case some data is missing. And in this phase, it's not necessary to use HDFS because the data is very huge, and invoking HDFS will have some more costs. It's not very good for the efficiency of your whole task. But now, in this case, it is possible that some data is missing because of some disk failure or network transfer failure, right? And so once some data is missing, and we just need to invoke that map task again. We just need to redo that map task to generate the missing data instead of using HDFS to guarantee the fault tolerance. And the reduced task, they don't have the advantage of data locality. I'm not sure if you understand why the reduced task don't have the advantage of data locality. For map task, we can move the computation to the data, right? So where the data is, and they are organized by blocks, right? And we just move the computation to the data. So there's some data locality. We can utilize the data locality to improve the performance. But for reduced tasks, they are different with map tasks because the reduced input is not the original input. They are the map output. And the map output are distributed to different mapper nodes. But the reduce needs to read the values, all the values for the same key. But all the values for the same key, they may distribute it to different mapper output, right? So as a result, the reducer tasks can only use HTTP to fetch the values for the same key from different mappers and then merge them as an input. So the output, finally the output reduce is stored in HDFS for reliability. This is because the final output of the reduced task is what we want to get. So they are stored in HDFS. And the number of reduced tasks is not governed by the size of the input. It's different from the mapper number of mappers. And you need to specify the number of reducers. So in your main class, you need to set job.set number of reducers to tell MapReduce how many reducers you want to use. Okay. And now let's look at the whole MapReduce framework again. So mapper, after the map output, actually we can also use combiner to reduce the local data. For example, in the second mapper, we have C3, C6. Now we can merge them as just one key value pair instead of two key value pairs, C9. So it's a combiner. So each mapper will have one combiner to combine its final output. And for partitioner, they are used when there are more than one reducer. So for example, in this job, we have 3 reducers. So each partitioner will compute a partition for each key. For A1, B2, for each key value pair, a partitioner will compute their partitions. So for example, A1 is put to its reducer. It's assigned to the first reducer. And B2 is assigned to the second reducer. And C9 is assigned to the third reducer. So the partitioner is used to compute the partition to decide which keyword pairs is processed by which reducer. And then the shuffle and sort, again, they will group the values and sort the keys, and the keys will be sent to the corresponding reducer for processing. So this is a more complete MapReduce framework. Map and combiner, and then partitioner to compute partition, shuffle and sort, and finally reduce for doing the aggregation. Okay, so next I will use another problem as an example to explain MapReduce programming. But before that, I'm not sure if you totally understand the whole framework of MapReduce. And if you have any question, you can ask now. Okay.
On the intermediary results that say that they snap the map to HTML.
Yeah.
Where are they kept then?
I'm sorry?
Where are they kept, the intermediary results?
You use local file system to keep them, to store them. Your local file system.
Okay.
Yeah. Yeah. Okay. What's your question? Oh, okay, okay. Yeah. Store what? Sorry?
Store its own metadata. DFS is like an abstraction file system based on existing file system, right?
Not abstraction of existing system. So it's different from the existing system, file system. So it provides a
Distributed file system.
yeah, distributed file system. That's right. Yeah.
So it provides an abstraction, but I think it should have a
Some metadata.
centralized.
Yeah, you are right. There's one center node called master node to manage the metadata. For example, the files are still organized as a tree structure, right? Now, how the tree structure is stored, what is the meta information for the tree structure? There's still one master node to organize this information. You are right. Can fail. Yeah, that's right. If the master node fails, then your whole HDFS is cannot be used. That's right. But there's some mechanism to guarantee this. There's some recovery mechanisms to solve this problem. So if the master node fail, and you still can have some checkpoints to recover your HDFS metadata, and then to put them to a new master node to recover everything. Yeah. So for more HDFS details, we will still have about some lecture slides to explain them, to explain the internal mechanisms. But here, you just need to know how you can use HDFS. Okay. Okay, so now let's look at this example, and I'll try to ask you to think about how to design some the MapReduce algorithm for this problem. Again, it's a very simple problem. And you can find this example in the textbook, the Hadoop, the definitive guide. There's some more details if you want to get more information. So this is a weather data set, and it's from the National Climatic Data Center. It's a large volume of log data. It's a sensor data. It's a lot of weather sensors. And what we care about here, we only care about the temperature. And the data format is like this. It's a long line. And in this long line, and each record has a lot of elements, a lot of attributes. And we only care about the temperature. So now in this long line, what we need to do is to get the year, and we need to get the temperature. So the data files are organized by date and weather station. And there are also a directory for each year from 1901 to 2001. And okay, so the question is that given you such a large data file, so what is the highest recorded global temperature for each year in the data set? Again, this should be a very easy task on a single computer if the data is not very huge, right? You just need to read each line, and then from each line, you extract the year and temperature, and now again, you can use a hash table to record the current highest temperature for each year, right? Now for one line, when you process one line, you can get the year and get the temperature, and you look up in your hash table to see if the year is already in the hash table. If it is not, you just put the year and temperature into the hash table. And otherwise, you can check if this temperature, the new temperature, is larger than the existing highest temperature, then store the higher one. So that's a very easy task if the data is not large on a single computer, right? So besides using some program language, you can also use some other tools to analyze the data to get the highest temperature for each year. So for example, this one example of using the awk is a tool to do this task. And finally, you can get these results. And in the textbook, they said that they try to use this awk program, this tool to get the results, and it took about 42 minutes on a single EC2 high CPU extra large instance. 42 minutes. Remember this number, okay? And the process is just like what we have discussed before, right? Just get the year temperature and then compare the temperature with the current highest temperature. So it's very easy. But now, let's think about how we can use MapReduce to do this. So again, without MapReduce, it's very hard to parallelize this work, right? So first, we need to think about how we can divide the data and how we can divide the work into even distribution. Because load balance is very important. If the load is not balanced, then the parallel processing is not meaningful. So the power of the parallel process is because we can achieve some load balance. So then it is expected that we can have a better running time. And how to combine the results is also very complicated because the results are from different nodes, right? So we need to exchange the data from different computers, and also even just on a single machine, the local data may already beyond its computation power. So anyway, so there are just a lot of problems, a lot of challenges to deal with. But Hadoop can take care of these issues for us. So we don't need to care about these low-level, system-level details. So now, for you, this is a new problem. And given you a problem, you need to design a MapReduce algorithm. So what you need to think about? So normally, you need to think about the following questions. So first is about what should be the data format, what should be the input key and value, and what should be the output key and value data type. So this is actually the most easy task, but this data type decides what you can do in the next few steps. For example, next you need to decide what does the mapper do, and what kind of output should the mapper generate. And next is that if we can use a combiner to improve the performance, and if there is a partitioner required, if we use more than one reducer. And also, the most important thing is, another very important thing is that how to do the data aggregation. That is what we can provide in the reduce function. Okay, so these are the questions we need to think about. And what are the file formats is also very important. So so far, for example, the word count, and also in this task, we use the text files. But sometimes we may use binary files, so we also need to deal with different file formats. So we need to think about these questions and then to design our MapReduce task. For the MapReduce data types, it's very important that your reduce input and the mapper output must be consistent. So here, the key type and the key type must be the same, and value type and the value type here must be the same. This is very important. And considering the combiner function, and remember that combiner function, it performs the similar tasks as a reducer. So it takes the mapper output as input. So as a result, the key format must be also the same as a mapper output key. And the value, input value, must be the same as a mapper output value. And the output of the combiner will be received by the reducer. So as a result, the output key must be consistent with the input key of reducer, and the output value of the combiner must be the same as the reducer input value. So this data format, it must be consistent. Otherwise, you will get some exceptions, and your job cannot be finished. And for the partitioner, and it's like this: you get one key and a document, and according to the key, you compute partition number, which is an integer. Okay, so next is about the MapReduce design, and you need to identify the input and output of the problem. So, for example, the input is a long line, right? And so the key will not be used. It's the same as same as in the word count problem. So the key is not used. So it's okay. We can just use object as a key, and this long line is a string. We can use text as a string. So it's an input, and for the output, what we need to get is the year and temperature, right? So the year could be string or integer. It doesn't matter because year is just for characters. So using string or integer, they can have the same they have the same size. And for the value is maximum temperature. Okay, we can use integer. So now it's input and the final output. So next we need to think about the MapReduce, the mapper and the reducer. Consider these two components. Okay. About data types, there's so here are some more details. What we have seen so far is just text and iterable. So text is a wrapper for the string, and iterable is a wrapper for the integers. And here are some more examples. For example, boolean, byte, short, int. They all have some corresponding wrapper classes in MapReduce. So if your data is in the basic data format in Java, then in MapReduce, if you want to write the data to HDFS, to the file system, you need to use the corresponding classes to wrap them and then use them in MapReduce. Okay, so next is your task to think about what does the mapper do and what does the reducer do. And we can have the next break, and after the break, so let's discuss your ideas.
I want to know how to passing the job through the nodes.
Pass the jobs. When you have assign the jobs.
Yeah. So this means they assign the same Java file to each node.
So first, the data is distributed to different computers according to the standard. And then Hadoop MapReduce will move the other side, move the computation to the data web page. That means it will put the Java file to the corresponding computer, and then make Java file run on that computer and reads corresponding data as input.
So this means if I use a library to do some calculation in the job file, so it will require the every node in the network have the same library, so they can call the.
First, you just need to compile your Java file on one computer, right? So on this computer, you have all the libraries, and then a single Java file will be compiled. You just need to use Java file to all the computers. The libraries are not. You don't need to put all the libraries across the whole cluster. It's not necessary.
You said the key needs to be hashed. Yeah. So it means that every type of the key. You mean you said the key can be every type. Yeah. So the class or the class of the key needs to be hashable.
I think the Java actually define a Java class, and by default there's a hash code function, right? This hash code function is used to get the hash code for this.
So you need to define. You need to define the hash. Because not every type of class is hash. Like you define your own class environment. But I'm not sure in Java.
In Java, so every class is extended from the object class, and object class has one hash code function, which means that you always have a hash code for the class. And sometimes you can override this hash code function, so you have your own hash code for.
Because I'm more familiar with the Python.
I see that.
Okay. Many Python.
Okay. HDFS is used to perform the whole process. Yeah. Yeah, thanks. Yeah. That's why it's called distributed process. It's not hard. Distributed process. How do you yeah. This is not so HDFS is it's kind of abstraction of the one of management. Okay. It provides the operation of the but it's built on top of water. So you see how a data is first HDFS tag with the master node. So this master node has all the basically all and then
where
it's very many sources. For example, in labs, the files are first called in a local software. For using the HDFS comments, HDFS tools. that has to be received is the test. And you have how many blocks of file and then assuming that n blocks. Okay, so that will contact all the computers. So how many blocks we have, how many blocks we have, and you have 2 blocks of that, and you have 3 blocks of that, and you have 3 blocks. Something like this. That's a low level detail. So you can think about it as let's provide you a single normal file. At the lowest level, lower level, you would upload more. Possibly for computer. Again, it's answer it. No, there's no combination. That's the rate of the file. That's for answer computers. There's no final combination. So each reducer must consider one of the files. Yeah, that's right. That's often very high. If you want to work on, you need to rate them from the test and number them. But you also do not reduce the change. So you just reduce out. You can check in the net for the example, and some can set number reducer like 3, and you see 3 files.
That's the final result.
Yeah, that's the final result.
Okay, so let's continue this problem. So let's look at the problem again. What we do, what we have is such a log file, right? And what we want to achieve is to get the maximum temperature for each year. So now the question is, my question is, what does the mapper do according to your current understanding of the MapReduce using with count? To see if you can design a MapReduce program for this problem. So what does the mapper do? So the input is this line, right? Then you get the year and temperature. So what is the output for this line? Yeah, that's right. So the mapper is very easy, just the year and the temperature. Yeah. For the mapper, it's just a transformation. Just get the information we need, the information that will be useful for the aggregation. Okay. So for the mapper, it's very easy. And we just pull out the year and the temperature. So in this example, we also need to deal with some other problems, such as the bad record. We need to have some filtering. But for the normal record, we just need to do like this. We extract the year and temperature. So for example, the first line is 1950 and 0, and the second one is 1950 and 2022. And in the first phase, after the map phase, for such an input, data chunk, input split, the output is just like this, the year and temperature. So that's our output of the mapper. And next so given such map output, so how to do the aggregation? So what does the reducer do? So what will the reducer receive? What is the input of the reducer? The key is the year, right? And the value? Yeah, list all the temperatures. That's right. So now, given the input, it is very easy to identify how to design the reducer. We just select the highest value from the list of temperatures. So that's it. And for the mapper, okay, so you decide input and output is a year value, and that's it. And for the reducer, okay, you get the input as year and a list of temperatures for this year. And now you scan all the values received for the key and then find out the maximum one. So that's it. So you finish. So for example, this is a mapper output. And after the shuffle and sort, they are grouped like this, right? And the reducer function will receive this mapper output, the grouped and sorted result, and then do the aggregation. So finally, you have this 111 and 22 for this year. So you have this as a final output. So that's it. Okay. And for the code, okay, it's very actually it's very easy. The textbook Hadoop definitive guide, they provide all the code for you. So also some sample data. You can try them by visiting the provided links. So I just highlight the most important line here. So we aim in the mapper, we emit the year as a key, temperature as a value. As I said, in the reducer, we get the maximum value from all the values in this list. And then finally, we write the key, which is the year, and the maximum value as the final output. So in the main class, so we need to configure the job and then specify the output type and then start the job. So you can get the code from this from this page. Okay, so my question here is that why the combiner class can just be set as a reducer class? Why in this problem, we can also use a reducer class as a combiner class? So actually, I have already shown the answer to you, right? So remember that slide. It is because now this aggregation function is a max. Because max is commutative. Max AB is equal to max BA. And it is also associative. So that's why here we can just use the reducer class as a combiner, and that's it. And that's about combiner. Now how about the partitioner? Do we need to use a partitioner? Yeah. But in this problem, actually, it's not necessary to use a partitioner because this task does not require us to do anything about the year. But if they ask to, for example, they ask us to group some years into one file, then we must use the partitioner to control this, to control that these years must be grouped in the same file. Yeah. Okay, so here's some more. I try to repeat the procedure for MapReduce when dealing with large data sets. Okay, so the data are stored in HDFS. They're organized as blocks, and then remember that the Hadoop MapReduce divides the input into fixed size pieces, which is called input split, and each input split corresponds to one HDFS block. Normally, it's like this, and for each block or each input split, the Hadoop will create one map task. And within each map task, so the map function will be called for each key value pair. Okay. And next, we will utilize the data locality to optimize our job execution. So we will run the map task on a node where the input data resides in HDFS. We move the map task to the data. And so actually, this is the reason why the split size is normally the same as the block size, because if one split covers two blocks, then it is hard to move the computation to the data, because these two blocks may not be stored on the same computer, right? In that case, we need to move this map task to different computers, which is very complicated for the MapReduce framework. So normally we just make sure that one split corresponds to one data block, and then we can move the map task for this block, for this split. And the map tasks write the output to local disk, not to HDFS, and then the reduce task don't have the advantage of data locality. So the input to a single reduced task is normally the output from all the mappers. So the reduced task need to fetch the relevant data from all the mapper output by HTTP. And finally, the output is stored in HFS. So the number of reduced tasks is not governed by the size of the input, but specified independently. So just try to emphasize the important things for you again. And here is a more detailed data flow of MapReduce. So let's look at this. When there are multiple reducers, so what we can do. So in this example, in this figure, assume that we have 3 data splits and we have 2 reducers. Now for each split, and we need to use one mapper to process that data split. Okay, so we have some for this split, we have one mapper task. Within this mapper task, so each map function will be used to deal with one key value pair. And locally in this phase, there we have some local sorts and also partitioned. So because we have two reducers, right? So we need to decide which key is processed is sent to which partition. So according to a partitioner, each key is computed. We need to compute the partition number for each key. So finally, we have to partition the keys into 2 parts, to 2 groups, and within each group, they are also sorted. So that's mapper output. So this is because we have 2 reducers, then we need to have 2 partitions for the mapper output. And optionally, you can also have a combiner in between. The combiner will combine the mapper output. And this is a local aggregation. So this is a mapper phase. And now this is a reducer, reduced phase. So in the reducer, first, because for the same key, all the values for the same key should be processed by the single reducer, right? So for example, one key, the reducer needs to get all the values for the same key. So as a result, the reducer needs to go to all the mapper output to fetch the data. So there's a partition from the first partition from this mapper, and the first partition from the second mapper, and the first partition from this mapper. And similarly in this reducer, also he needs to go to all the mapper output to fetch the second partition, and then merge them for each key as the input for the reducer. And some keys are processed by this reducer, and some keys are processed by this reducer. And finally, so they will be, the final output will be stored in HDFS. So it's a final replication, the final result. HDFS, in order to guarantee the fault tolerance, then they will replicate the results. So using replication to guarantee that the data missing or some failures will not cause problems. So this is more detailed MapReduce data flow when there are more reducers and for large data sets. And the key points, first, data is split into several input splits, and each mapper task is invoked for each split. And then the mapper output, you can have a combiner to combine them to reduce the size of the intermediate data. And the partitioner will compute a partition number for each key. So this is a key space partition. And within each group, and the keys will be also sorted. So in the reducer side, the reducer will need to read all the mapper output, the corresponding partition for him. And for example, this first reducer reads the first partition from all the mappers, and the second reducer reads the second partition from all the mappers. And then, because they are already sorted within the group, right? So they can just do a simple merge. And this simple merge is just of linear complexity. It's very easy to merge the output from different mappers. And then each key and the list values will be processed by one reduce function. So it's MapReduce data flow. So let's look at the data flow into more details, and it can be shown in this figure. So we assume there are more than one reducer, and the data is split into many splits. But we just focus on this figure. Just focus on one input split and one reduced task. So what is the detailed process? So assume that we have 3 reducers in this example.
This is one input split, okay? And then the mapper is used to deal with this input split. And each record is processed by map function and generate a lot of key value pairs. This is intermediate data and a buffer in memory. And next, they will be partitioned, sorted, and spilled to local file system, to local disk, not to HDFS. And the partition is like this, and we have 3 reducers. So the whole key space is partitioned into 3 groups, right? And for each partition, they will be sorted. Each partition they will be sorted. So this is the first partition. The first partition will be fetched by the first reducer, and the second partition here, it will be fetched by the second reducer, and the third one will be fetched by the third reducer. So this is about how the data are sent to different reducers. And this is all stored in local disk, in your local file system. And next, in the reducer side, so the reducer will read the relevant partitions from all the mappers. So for example, this is from this mapper, and this is from the second mapper, this is from the third mapper, from the fourth mapper. And then next we'll do the merge to merge the values for the same key into a single list. Because the input of the reduce function is one key and one list, right? But now they are from different mappers. So the same key and values may distribute it to different mapper outputs, right? So from different mapper outputs, they have a lot of key and a list of values. So they need to merge the list of values for the same key as a single list. So this is this merge step. In fact, this is also a sort. So we can see the sort happens in both the mapper task and the reducer task. So the mapper, this is a local sort for the local mapper output. And for the reduce task, it is a merge, but it can also be viewed as a sort because we also need to merge them according to the orders, according to the key orders. So this is also kind of a sort phase. So actually it's hard to say shuffle and sort is belongs to map or belongs to reduce. So it's kind of in between. And this is a more detailed data flow from mapper to reducer. So in mapper, and the combiner will combine the input split, it will combine the mapper output, and the partitioner will compute partition for each key. So here is the sorted key value pairs, and these key value pairs are for the first partition, and these key value pairs are also sorted for the second partition, second reducer. In the reducer side, the reducer needs to read the partitions, the relevant partitions from all the map output, and then merge the key value pairs, and merge the key value pairs and into the required input format, and then process them. So that's the whole detailed procedure. This is very important for you to understand MapReduce framework. So in the textbook, there are more explanations. So I hope you can, if you can't understand these details, you can read the textbook to get more information about the 2 figures. The 2 figures are very important for you to understand the data flow and the internal mechanism of MapReduce, and about how MapReduce do map jobs, do shuffle and sort, do group by, and do merge, and do the reduce tasks, and do the final output writing. Okay. So far, it's about the MapReduce programming introduction. I used 2 examples, word count and this highest temperature. And hopefully you can have a basic understanding of MapReduce programming. So from next week, you will begin to practice MapReduce problems in the labs. I will give you about 3 to 4 problems for you to have a try. And so far, if you have any more questions, because otherwise we will move to the next topic. Okay.
So during this task, merge the data? So is it the local disk or the?
You mean here?
Yep.
Yeah, the local disk.
Still the local.
It's still the local disk.
Is it supposed to pull the partition data via HTTP?
Yeah.
Right?
Yeah.
And then it stores it on a local disk
Yeah, on the reducer's local disk.
and writes to HDFS. Is that what happens?
No, the final output is written to HDFS. Here it's just to merge the data from different mappers and as a required input format for the reducer task.
And it all happens in a local.
Yeah, this part happens in the local disk. They are also not using HDFS because there's too much overhead cost by using HDFS. It's not necessary. Just use local disk is already enough. Okay.
But the output is in the.
Yeah, it's in HDFS. So input, output, they are in HDFS. But for the intermediate results, they are all in local file systems, local disk for each computer. Because the map task is in one computer, reduce task may be in another computer. So for this computer, just use local file system, their local disk to do these things, not HDFS. Okay. Okay, so if there's no more problems, I will move to the next topics about MapReduce algorithm design patterns. So previously, just two very simple problems. Then from now on, we will see some more complicated problems, and we will learn some very useful design patterns for very typical problems. So later, if you see some problems, you can think about if we can use these patterns to solve the given problem. So the first one is called the in-mapper combining. And the idea of this in-mapper combining is to, again, it's just similar to the combiner, is to utilize local aggregation. Okay, so why the local aggregation is very important? Because ideally, if the algorithm and the framework is scalable, so if we have twice the data, then we should have twice the running time. And if we have twice the resources, we should have half the running time. But normally it's not, we are not able to achieve this because first there's some cost on the network communication, right? And also we need to do something on the data synchronization. The network communication, because we need to do some data synchronization. We need to transfer the data. We need to exchange the data across different computers. And this will affect your performance. So that's why we need to try to improve the communication, so we can reduce the size of the data that need to be transferred across different computers. And if we can avoid most of the communication, then we can improve the efficiency a lot. So that's why we need to utilize local aggregation to improve the performance. So again, let's look at this word count example. This is a baseline, right? We have seen this before. So what's the impact of combiners? So combiner combiner works on the mapper output, right? So the key value pairs for the same key, if that they will be merged, they will be combined together. And now let's look at if we can use some more local aggregation mechanism to improve the performance. Let's look at the first version, another version for the mapper. So assume that we have another mapper. So the mapper is like this. So for each document, previously what we do is that once we meet one term, we just emit this term and one, right? And by using combiner, so after all the key value pairs are generated, then the combiner will combine the term and one values for the same term. And if there are two, for example, Hadoop 1, and then the combiner will make it as a one key value pair, Hadoop 2. So that's a combiner functionality. And now we can get rid of the combiner. We can do the in-mapper combining instead to improve the performance and to achieve the same result. So let's look at if we can do this by using this mapper. For a document, then we create associative array of also we can just you can just assume this as a hash map. We create a hash map for this document, and then for each term in this document, now we check if this
term is already contained in this hash map or hash table. And if it is not in this hash map, then we create a new entry for this term and with value 1. And if it is already in the hash map, we just increase the frequency by 1. And finally, after the document is processed, we emit we iterate over this hash map or hash table and to emit the term and the corresponding count within the document. Okay. So is there any problem? No problem, right? It should still produce the correct result. But if the combiners are still needed, given this mapper, yes or no? Just give me the answer, yes or no. No? Why? Yeah. But there's a trap here. In fact, you still need a combiner. Why? Because you can see where this hash map is defined and what it works. So again, remember the whole procedure, okay? The mapper produces a data chunk, and each map function produces one document. And the combiner works for all the mapper output, not just for one document output, okay? So if you do like this, you still need a combiner because this is a local aggregation, but this local aggregation is just for a single document, but not for the document in the whole data chunk, in the whole split. So what is the correct version? This is the correct version. Let's look at. You need to initialize a hash map for all the documents processed by this mapper. So you need to initialize this hash map here. And now in the map function, it's just to do similarly as before. And now finally, after all the documents are processed, and you iterate over this hash map and emit the term and the frequency. So in this case, okay, this is called the in-mapper combining. So in the mapper, within the mapper, we use a local data structure to preserve some data statistics for our job across all the documents. So it's kind of a combiner task, but now we explicitly describe how we will do the local aggregation. Okay, so we tell MapReduce in the mapper right, I will use such a data structure to aggregate the relevant information locally, and then finally I will emit all the information out to the to the disk. So this is called in-mapper combining. And in this design pattern, is what we do is like this. We follow the functionality of the combiner into the mapper by preserving the state across multiple map calls or across all the different documents. And the advantage is that it's much faster than using a combiner, because if you use combiner, remember that your mapper is not changed, right? So your mapper still need to generate a lot of key value pairs first. And these key value pairs, although they are buffered in memory, but they still cost some space and still cost some processing, they still have some processing cost. And the next combiner will process this mapper output to reduce the size. But in the in-mapper combining, this phase is avoided. So it uses memory to preserve all the required information, and then finally emit the local count, the final local count to the reducer. So that's why it is even faster than using a combiner. But the problem is that now you need to manage the memory by yourself, and you need to estimate how much memory you need to use for your job. And it is possible that sometime maybe your data set is very huge and your memory on a single computer is not enough to hold all the preserved data. So if in that case, you can't use this mechanism, you can only use combiner. And for
if you, according to your estimation, then your problem, your job will not cause this problem. Then you can use in-memory combining to improve the performance. And also, it's some potential for order-dependent bugs. But so far, our problem does not need to consider orders of the keys. But if the orders, which means that the order of emitting the key value pairs, if they affect the final results, then by using the in-memory combining, you will still meet some problem. Okay, so for the combiner, let's have a review. I have shown this slide to you before. So the combiner design is like this. Hopefully you can have a better understanding by this stage. The combiner and reducers, they share some ideas. So they have some similar aggregation methods, but sometimes they can be used interchangeably, which means that the reducer class can also be set as combiner class. But normally you cannot do that because if the function in your aggregation is not commutative and associative, if you do that, you will meet some problems. So we will see an example later. And Hadoop, it does not guarantee that how many times the combiner will be called for your job. So this is just optimization. It may be even not be called. So your algorithm cannot be, the correctness of your algorithm can't depend on the combiner. Okay, so which means that if you want to use combiner, you need to check if you remove the combiner and add the combiner, if the flow of your algorithm, of your program is the same. If it is not the same, then which means that your program has some problems. Okay, so for the problem, if it is commutative and associative, then you can use the reducer class as a combiner class. But if it is not commutative and associative, you can't do that. You need to write a separate combiner, and you can't use the reducer as a combiner. Why it is like that? Because for the combiner, it's kind of, this is the result of sum of the map output. So you're trying to apply the aggregation method in the combiner over the different map output to generate the final result. And only if the result, the function is commutative and associative, then you can have the same result, which means that you can do this operation by arbitrary orders. You can group them arbitrarily, and you can also, the order of how to process them is also does not affect the final result. So you can always get the same result. But if it is not like that, then your aggregation method in the combiner will cause some problems. So let's look at this problem. So this problem is to compute the mean. And so the problem definition is like this. You are given a lot of key and value pairs. And each key has a lot of values, right? So the data format is a key value. Is a lot of key value pairs. And your task is to compute the average value for each key. Okay. Now it's not the count, the sum. So word count is the sum. And it's also not the maximum. So in the temperature problem, it's a maximum. But here it is a mean value. It's an average value for the same key, for all the keys. Okay. So how we can do this problem in MapReduce? And the mapper, again, is very easy. So we just emit the key and the value to the reducer. And the reducer will receive a lot of list of values for same key. And now in order to compute average, so you need to iterate over this list and compute the count and compute the sum. And average is obtained by divide the sum by the count, which is average. Right? So this is a very easy MapReduce task if we just extend from the previous problem, from the word count problem or from the maximum temperature problem. Now let's look at how we can add a combiner for this task. Can we just use the reducer as a combiner? So yes or no? No. Why? Two things, commutative and associative. So is it commutative?
but it is not associative, right? For example, in order to compute average of 1, 2, 3, 4, 5, you can't do like this. You can't first compute average of 1, 2, and then compute average of 3, 4, 5, and then compute average of the 2. That's different. And in this case, you can't use a reducer as a combiner, because now if you use this reducer as a combiner, so then your program will get different results in different runs. Because in this run, then your order is like this. In another run, your order is like that. Then for different runs, the results are different, right? So you can't get the correct result if you use this reducer as a combiner for this problem. So that's why it's very important to identify if this aggregation function is commutative and associative. If it is, now you can use this reducer as a combiner to improve performance. But otherwise, if it is not, like this problem, you need to define your own combiner instead of this reducer to do the local aggregation, to do its combiner. Okay. Now how can we design a combiner for this? So obviously, the reducer can't be used as a combiner. But how to design a combiner for this? So the combiner will receive the key and the list of strings as an input, right? But what should be the output of the combiner? Okay, because of time, I can show you one answer. Let's look at this. If it's correct or not. So we don't change the mapper. It's still emit the key and value, and then the reducer is also it's changed a little bit because in the combiner we have received the key and the list of values. Remember, this is a local list of values for this key because the combiner works on the single map output. It's just a local aggregation, so there's a local values for this key. And what we do here is that we count the sum, local sum, and the local count. Then for this key, we emit this key and the local count, local sum to the reducer. And the reducer receives this, and then I add them together and then do the average. So is this correct or not? It seems correct, right? But it is not. Why? Obviously, it's not. I can't show you the answer directly. Why it is not? So remember, previously I have said that you need to guarantee that your program will not be affected by the combiner, which means that after removing the combiner, your program can still be run by MapReduce. Okay, so let's try to move the combiner. Let's remove the combiner. Now look at the mapper and the reducer. The mapper is in this format, right? Key, integer. But the reducer receives key and pairs. Obviously, this is not correct, right? You can't design a program like this. So if you do this, then you will receive some data mismatch exception because your reducer cannot identify your mapper output because what your reducer expects is pairs, but now what you emit is just a single integer, right? So the logic seems correct, but the problem is that you cannot write a program like this. Okay, so what is the correct version? And yeah, that's right. You need to change the mapper. You need to change the mapper format like this. You need to change the mapper from a single integer to a pair. That's very smart. And now, okay, let's look at this program. So mapper, reducer, yeah, now it works. So without the mapper, without combiner, what your reducer receive will be a list of pairs and with a value and ones, right? And so the reducer can still work with that given input. But with the combiner, your value and ones will be locally aggregated as a sum, local sum, and local count. And the local sum, local count will be contained in the list of pairs here for the reducer as a reducer input. And now reducer will process this input and do the aggregation to compute average. So now this is the correct version of doing the combiner design for this average problem.
So using this example, I aim to let you know that when you design a program, it's very important to see if the combiner will affect your program or not. If it affects your program, then it means that you must have some problem. You need to fix this problem. And otherwise, then next, you still need to further check if there are some more problems. But at beginning, at first, you need to guarantee that the existence of the combiner will not affect the correctness of your algorithm, of your program. Okay, so this is about combiner. Now the question is, for in-mapper combining, we don't need to use this combiner. So how can we use in-mapper combining to get rid of this combiner, but still generate and produce the correct result? So let's go back to the word count. So this is the correct version, right? We need to maintain an extra data structure. It's a hash map. And so this hash map will be used to preserve some data across all the documents, across all the records in the data input split. So similarly, for this problem, given this combiner, we can do similarly. But if we can just use one data structure to do that. Okay. So next week, you will need to practice something similar with this problem. And the answer is like this. So just a pseudocode, how to do the implementation, you still need to spend more effort, okay? So in this problem, for the average problem, we need to use two data structures. We need to use two hash maps. One is used to maintain the local count. Another is used to maintain the local sum. And then finally, we will emit the pair. And the pair is obtained from both the local count and the local sum hash map. And this will be sent to the reducer, will be fetched by the reducer. So this is in-mapper combining version for the average problem. And so you can see the difference between the combiner and using the in-mapper combining. The combiner uses another combiner class, and your mapper is not affected. So your mapper still generates the output as without the combiner. And the difference is that combiner will work on the mapper output to reduce the size of intermediate data. And for the in-mapper combining, so you don't need to first generate all the key value pairs and then do the local aggregation. So instead, you will use some kind of a buffer in memory to preserve the state of the data across all the records in the data chunk, in this input split, and do the emit finally after all the records are processed by a mapper. Okay, so how to do the implementation? This is very important to know that the life cycle of the mapper and reducers. The life cycle of them is like there's a setup, there's a initialization, and the map function. So what we see before just the map function, but actually there's a setup function and also cleanup function. So the setup function is used for the initialization, and cleanup function is used for the some tasks at the end of your mapper task. So we do not need to invoke them explicitly. So MapReduce will do that for us. And in mapper combining, we can use setup to initialize the data structure for the data structure to preserve the data state, and use cleanup to emit the final key value pairs. So for example, in this word count problem, we use it in mapper combining, right? And here we can initialize this data structure in the setup function. But also, since this is just a initialization of one data structure, you can also do this just before the map function. It's also okay. You don't even need to use the setup function. But this part, for the key value pairs image, you must use cleanup function. You need to iterate over this hash map and then emit all the terms with their local count to the file system for the reducer to fetch. You need to do this in the cleanup function. Okay. And the reference from today's lecture is from this chapter 2 of this book and from chapter 3.3 from this book. So if you are not quite sure with some part of the lecture slides in today's lecture, you can refer to the two textbooks for more details. Next week's lab is about word count and the in-mapper combining. So hopefully you can try yourself to do the programming. But I know at the beginning it's very difficult because you are not familiar with MapReduce programming. So anyway, so the only way is to do more practice. So I will try to give you enough problems for you to practice before the first project, because the first project is still a little bit complicated. You need to spend at least 3 weeks for that problem. Okay. So see you next week.